Hello everybody. I hope you've all had a really lovely half term. Hope you haven't done too much work. I hope you've enjoyed the sunshine. I certainly have. Welcome back. We're now into the final 7 weeks of year 12. As no doubt you know from Mr. Miller's letter to your parents, the government has decided that no secondary school children will be back before the 15th of June at the earliest. And even when we get you back, it will only be a maximum of a quarter of year 12 at any one time. So that obviously you're not going to be in every day. And there'll be a limited amount of lessons that you will be attending throughout the week. So a couple of decisions have been made. Number one, which hopefully has been communicated to you, is that there will be no assessments at all this half term. Woo! So hopefully you're quite happy about that. In return, end of year 12 exams will now take place at the end of September. That will give us obviously a couple of weeks once we get you back in September to do some review and some revision, and then you'll have your end of year 12 exam that you would normally have had about this time of year. Okay, so bearing that in mind, what I want to achieve with you over the next 7 weeks is to get ahead and do a little bit of year 13 material. So we're going to continue with organic chemistry. We're well into that. We've been doing it since Christmas now. We've done 4 different functional groups so far. We've done alkanes and radical substitution, you know the mechanism for that. We did alkenes. We've done electrophilic addition, you know the mechanism for that. Also with alkenes also talked about polymerization and addition polymerization, where the double bond breaks and all the monomers add up together. We've also talked about alcohols, and they have quite a few reactions. So oxidation, where first of all the hydrogens are removed from the OH and another hydrogen from the same OH to make the C double bond O. We're going to come back to that today because today's topic is all about carbonyls. And then again, second stage of oxidation, where then oxygen adds in and we make a carboxylic acid. So so that's oxidation of alcohols. We also talked about dehydration or elimination of alcohols, where the OH is taken off, plus a hydrogen from an adjacent carbon and makes a double bond, makes the alkene. What other ones have we done? And we've done substitution with an alcohol, where the OH goes off and a Br or a Cl comes on. Okay, so that's alcohols. And then the final functional group that we've done so far this year is haloalkanes. Those are the ones where, like an alkene, the hydrogen's been removed and it's been substituted in with a bromine, a chlorine, a fluorine, or an iodine with a halogen. Okay, and with that one, the main reaction that you need to be aware of is nucleophilic substitution. So where you've got your alkene, no, it's not your alkene, your halogen being taken off and being replaced by an OH. And you know the mechanism for that one. Okay, so today we're going to start carbonyls. I'm going to do it over 2 weeks. Today we're going to talk about what carbonyls are. We already know, by the way. They're aldehydes and ketones. We've come across these before. This is not new, okay? And we're going to talk about the reactions. Next week, I'll talk about testing for them because it's a nice little test. I'll set you up some YouTube clips and things like that. And then give you some more questions on the whole topic of carbonyls next week. So today's lesson is relatively straightforward, okay? I'm going to introduce the carbonyls, aldehydes and ketones, talk about what they are, how we name them, talk about their reactions. There's 3 reactions, one of which you already know, and the other 2 are kind of related, so it's not difficult. And then I'm going to give you some very short questions today on just checking that you've worked out what the products are of the reactions, okay? So that's where we're going to do. Right, so I'm going to share my screen so that you can see the PowerPoint that I have sent. Can you see that? Let me make me a little bit bigger in the corner. Is that okay? Right, okay, so hopefully you can see this now. So this I've also sent to you, and it's up in our file on the Microsoft Teams, on our Microsoft Teams. So carbonyls, really useful group of compounds. They're the ones that give us solvents. Any females in my classes will know, you know, when you want to take off your nail varnish, when you've had pretty nails. I never have pretty nails, but if you ever have pretty nails, you take them off using propanol. It's a ketone. They give us flavorings, perfumes. So they're really important group of compounds. Okay, so how do I get this to move on now? Do I click? Gosh, there we go. Right, so quick reminder, okay? So where do we get carbonyls? We generally get them from alcohols, okay? So remember, alcohols, a little bit of revision. So we have 3 different kinds of alcohols: primary, secondary, and tertiary alcohols. If we have a primary alcohol, the OH is joined to a carbon that is only joined to one other carbon, so it must be on the end of the chain. If it's a secondary carbon, the OH must be in the middle of the chain, because the OH is attached to a carbon that is attached to 2 other carbons. So it's the middle of the chain. Tertiary alcohol has the OH atom, so the OH group, bonded to a carbon atom that's joined to 3 other carbons. So that would mean that it must have a chain, it must be in the middle of the chain, and then off the same carbon that the OH is on, there's also a branch. Okay, so remember how alcohols react. You should already know this. You should be quite confident with this, but this is just revision. So the only bit that we need to be worried about today is oxidation. Okay, so if you remember oxidation, way back to GCSE, oxidation is the gain of oxygen and reduction is the loss of oxygen. Remember oil rig, oxidation is the loss of electrons, reduction is the gain of electrons. And then what we learned last term is oxidation is the loss of hydrogen, or reduction is the gain of hydrogen. So these are my definitions of oxidation. So when we oxidize alcohols, we have both, hang on, can I go back? Does it allow me to go back? Yes, it does. So with oxidation of alcohols, we're concerned with both this one to start with, but also this one. We're not worrying too much about this bottom definition for the minute. Okay, so primary, secondary, and tertiary alcohols all react differently when we oxidize them. We use an oxidizing agent. Remember this one, potassium dichromate, acidified. It's got loads and loads of oxygen, 7 oxygens. It can easily lose the oxygens and give them to the thing that needs to be oxidized. So that's what makes it such a good oxidizing agent. This is orange in color, and when it is reduced, it turns to green. Okay, so once it's done the oxidizing, it goes green. And that's one of the ways that we can test whether oxidation has happened or not. Add the acidified potassium dichromate. If it goes green, then we know oxidation has happened. Okay, can I move that one on? Right, quick refresher memory. If we've got a primary alcohol, here we go. Here's my primary alcohol. In fact, I'm going to do this one on my mini whiteboard at the same time, just to refresh your memories. Okay, so this is just revision at the minute. You've done this before, but it doesn't hurt to go through it again. Okay, and we're going to do this. So this is primary alcohols. I'm just going to stop sharing my screen for the minute. There we go. All right, so can you see that? So if I move across here a little bit, how can I do that? There we go. Right, so remember, first definition of oxidation is the removal of hydrogens. Where do the hydrogens go? They go with this oxygen. What's the oxygen going to make? It's going to make water. How many hydrogens does it need for that? 2. Okay, so it's going to remove, okay, so this oxygen is going to remove the hydrogen from the OH plus one other hydrogen that is attached to the same carbon that the OH group is attached to. So it's going to take that one, and that one, like that. And so one of my products is going to be water. Just going to put down there like that. And what am I left with then? Okay, I'm then left, this is CH3, like that. That's an H. That H is gone and that H is gone. So at the minute I've got that. Now that can't work because obviously I've got 3 bonds around here and the oxygen's also not happy. It needs 2 bonds going to it. So double bond in there like that. It makes an aldehyde. So the first step of oxidation with an primary alcohol is to produce an aldehyde. This is my carbonyl. Aldehydes are one of my carbonyls, okay? So this is the way that we make aldehydes. We have to distill immediately, okay? Otherwise it will, what will it oxidize further to? I'm gonna pause while you all shout the answer at screen. Yes, did you all get it? So once I've made my aldehyde, I can do a second step of oxidation. Let's just quickly go through that one. So if I've now got my aldehyde here, like that, just rub that all out. My new mini whiteboard pens are not as good as the school ones, but my school one has run out. Okay, here we go. So there we go, like that. There we are, like that. So there's my aldehyde. So it goes to set. So this is what I got from distillation. If I continue to oxidize it, remember, second step of oxidation is addition of oxygen. Where does it add into? It adds into there. And what does it make? It now makes a carboxylic acid. And there's my OH gone in there. There's my OH, like that. So primary alcohols, 2-step oxidation. First of all, to make an aldehyde. If you distill it and get rid of it straight away, if you don't and you allow it to continue to oxidize with the oxidizing agent, remember there's loads of oxygens in the oxidizing agent, so it will continue to oxidize if you give it chance. So if we do it under reflux and give it chance to continue to oxidize, it will then further oxidize to a carboxylic acid. Right, let's just quickly go through what happens with the secondary alcohol before I really don't like these new mini whiteboard pens. I might have to see if I can find another one which is better. Right, okay. So with the secondary alcohol, your OH is in the middle, like that. Okay, there's your H. I'm just going to do it like that just for easiness sake, like that. Okay, so along comes your oxygen from your oxidizing agent. Remember, oxidation is the loss of hydrogen. So what we're going to do, we're going to remove the hydrogen that's attached to the OH plus another hydrogen that's also attached to the same C. Okay, here we go. There's my 2 H's and an O. What does that make? It makes my water. It's my other product. What am I left with then? See if I can, I'm just going to draw it like that. So that hydrogen will have disappeared. Okay. And that hydrogen will have disappeared, like that. Okay, like that. And what are my products then? Quickly. It's really hard to rub this out. There we go. So what have I got then? So I've now got this, okay, that carbon's not happy, it's only got 3 bonds. That oxygen's not happy, it's only got 1 bond. So if we make a double bond between there and there, that is now happy. What's that made? That's made a ketone. That's my other carbonyl. So how do I make the carbonyls? I make them from oxidation of alcohols. If I want to get an aldehyde, I pick a primary alcohol and I oxidize that, distilling it straight off so that I get the aldehyde. If I want a ketone, I start with a secondary alcohol and I do it under reflux, because remember, can this one oxidize any further? Is there any way I can put an extra O in there? No, there isn't. So this is as far as it goes. So oxidation of a secondary alcohol gives me my ketone. Okay, I'm going to share my screen again so you can see the PowerPoint. Hang on, let me just do that. Right, so back to maybe a bit bigger in the corner. There we go. Right, so here we go. So this is what we've just been talking about. So there's my distillation, oxidation of a primary alcohol to form my aldehyde, okay, under distillation, so we don't allow it to go any further. Can I make it go further? I need to click this one on. Why is that not happening? Right, we're not happy here. For some reason, it is not allowing me to click. Hang on, let me just stop sharing for a second. What's happened here? Aha, now why is that not doing that? Right, we're going to try again. Screen share, portion of the screen. There we go. Let's see if we can make it work this time. Right, there we go. So oxidation is the loss of hydrogen. Why is it not letting me click on anything? I am clicking. Okay, that's fine. I'm having technical problems here. I wonder if I can do... Hang on. I might just sort this out a different way, hopefully. Let me stop sharing for the moment. And then if I screen share a different way, just see if I can make the whole of it. There we go. Sure. Here we go. Let's make that one a bit bigger. Make this one a bit bigger. Can I make that one bigger? There we go. Finally. Let me move me down into the middle here. There we go. Right, this is not ideal, but I don't know what's gone wrong. Technical things are not my forte, as you no doubt will have worked out by now. Right, that's as best as I can get it. I apologise. I don't know what's gone wrong with my screen. Maybe next time I freeze it, it'll behave itself when I unfreeze it. Okay, so let's go back to what do we have there. Okay. Oh, gosh. Where's my PowerPoint? I apologise for the problems that I've got with... Let me just get my PowerPoint back up again, because it's not behaving itself at all. Will not allow me to click on at all. So we're on to this one here. Right, can I make it... If I make it big, is that going to work? Oh, there I am. Oh, that's maybe better. There we go. Put me down in the corner there. As long as it works, I don't really care. Okie dokie. So there we go. So that's what we've been doing about. So primary alcohol oxidized makes an aldehyde. Okay. Okay. And then if I then continue, move me out the way. Need to put me somewhere where I'm not going to be in the way. Okay. So here we go. So I continue to oxidize. It will then produce my carboxylic acid. Okay. Then secondary alcohols. Here's my secondary alcohol. This is the one that we just went through, okay, makes a ketone. That can't oxidize any further, okay, so remember that, can't oxidize any further because there's no possible way that the oxygen can add in because the carbon's already got 4 bonds and it can't make any others. Okay, what about tertiary alcohols? What do we know about those? Yes, that's right, they don't oxidize at all, okay. So quick quiz, yeah, I'm going to pause so that you can answer these. What's the carbonyl group? Okay, fantastic. It's the C double bond O. If it's on the end of the chain, it's called an aldehyde. If it's in the middle of the chain, it'll be called a ketone. Okay, how can the ketone be formed? What we just said? Fantastic. It's the oxidation of a secondary alcohol with acidified dichromate, potassium dichromate. How about an aldehyde then? What do we need for an aldehyde? Hopefully you're playing along at home. Okay, fantastic. That's oxidation of a primary alcohol. Oh, why are they polar? What can you tell me about them? They've got a carbon and an oxygen. Okay, fantastic. The oxygen's more electronegative than the carbon, so we'll pull electrons towards the oxygen end, making them a polar molecule. Okay, fantastic. Right, we're finally on to the bit of that was just all revision. Find somewhere to put me where you can still see my whole screen. Right, so remember at the beginning of every lesson, I always go through what you're required to know from the specifications. This is now the year 13 specification we're into. So it says reactions of carbonyl compounds, including, okay, this bit we've already done, oxidation of aldehydes, using potassium dichromate acidified to form carboxylic acids. Then nucleophilic addition. Ooh, a new one, right? We've had radical substitution, electrophilic addition. We've had nucleophilic substitution, and now we have nucleophilic addition. Okay, so nucleophilic addition reactions of carbonyl compounds. There are two that you're expected to know, okay? This looks very complicated. It's sodium hydrido tetrahydridoborate, I think it's called. It's very complicated. You don't need to worry about it. It's a bit like my potassium dichromate. As you can see, it's got lots of hydrogen, so it's only the hydrogen that we're interested in. So we're going to use this to form alcohols, and then we're going to use this compound, which is a cyanide. So this is hydrogen cyanide, or sodium cyanide, with acid catalyst to form some compounds called hydroxynitriles. It's addition. What's addition do? Breaks the double bond and adds in. So we're going to be breaking that carbon-oxygen double bond in order for these reactions. And you need to know a new mechanism. Mechanism's very straightforward. It follows all the rules that all the other mechanisms you've ever done before are followed. So don't stress about it at all. It's not tricky. Okay? Right, a little bit about carbonyls. Okay, so the carbonyl group is the carbon double bond to an oxygen. Okay, the oxygen is more electronegative than the carbon, so that will make this a polar bond. This carbon will be slightly delta positive. This oxygen will be slightly delta negative. This carbon slightly delta positive. This oxygen slightly delta negative. Okay. So there we go, it's got aldehydes and ketones. Obviously, we've got a double bond in there. What do we remember about double bonds? There's a sigma bond along the plane in between the carbon and the oxygen, and then around the edges, there's overlap of p orbitals to make a pi bond. That makes it a weaker bond. It's easy to break, just the same way as we talked about when we talked about the alkenes. Okay? So that's all, again, very familiar because we've come across that before. Now, quick question. When writing out the structural formula of aldehydes, do you think we should write it as R being any alkyl group like CH3, and then COH, or RCHO? Right, I'm going to pause and let you have a think about that for a moment. What do you think? Which one looks better? Which one looks funny? Why does it look funny? Which one might make you think that it's something other than an aldehyde or a ketone? Okay, have you had a think? So hopefully you've kind of worked that one out. So both are, let me just get myself out of the way. There we go. Both are technically correct, but we tend to write it as CHO rather than OH. If it was OH, it would make us think that it was an alcohol, but actually I wouldn't have enough hydrogens around the carbon for it to be an alcohol, so we get a bit muddled up. So in order to prevent us from being muddled up, we tend to write it the other way around, CHO. This indicates that the C is connected to the H, and then the C is connected to the O with a double bond, rather than in this case where the C is connected to the O and then the H is connected to the O, okay? So either way, we tend to do this way. Okay, right, naming is very easy. You name the alkane, you drop off the E, and you add AL on the end, so you get methanol, ethanol, propanol, butanol, pentanol, hexanol, etc. Okay? They're really important chemicals. For biologists amongst you, they are in the rod cells in our eyes that help us to see. Methanol is also quite an important compound. We use it as preservative. You know, like those biologists amongst you, when you have like samples of, I don't know, frogs or eyeballs or whatever it is in jars, and then they're kind of floating in a liquid. That liquid is methanol. It used to preserve the samples and make sure they don't rot until you can actually have a look at them. And it's also used in manufacture of thermosetting plastics in polymer industry. Okay, so ketones. Ketones, again, naming them, we drop the E off the end of the name of the alkane and then add ONE. So we get Well, can we have methanone and ethanone? Is that possible? Okay, that's asking you a question. Think about it for a second and tell me why it's not possible. Okay, correct. Okay, ketones, remember, the carbon-oxygen double bond has to be in the center of the chain. So I've got to have at least minimum amount of 3 carbons in my chain in order for that to happen. So propanone is the simplest one. So propanone, butanone, pentanone, hexanone, etc. Okay. This is, again, a really common compound. Propanone, those of you who've ever used nail varnish, is the stuff about nail varnish remover. Okay, we also use it in the lab. It's the stuff that I have where if there's any graffiti, I always go around and wipe it off with the propanone. It's really good solvent. It dissolves permanent ink and gets things off. It's really useful. It also evaporates readily, so we can actually use it as a drying agent. If we've kind of got some glassware, swill around a bit of propanone, it evaporates really quickly and dries your glassware for you. Particularly, if you've got very thin glassware, like a burette or something like that, and you're wanting to dry the inside of it, it's a bit tricky, but you can use something like propanone in order to do that. And ketones are formed from the oxidation of what? Can you remember? We've just done it 5 minutes ago. Correct, secondary alcohols. Well done. Right, in terms of naming, obviously aldehydes, the carbon that the carbon double bond O is attached to has to be carbon 1, and then everything else numbers off that 1 carbon. It's the end. A bit like the carboxylic acid. Remember we said carboxylic acids, the carboxylic acid carbon is always carbon number 1. That's the same for an aldehyde. Okay, so that's always your carbon number 1. With ketones, carbon 1 is the closest end to the carbonyl. Okay. Right. I'm not going to go through these ones. You can go back after you've watched my video, have a look at these ones. There's some questions about drawing them, have a go at drawing them. Some questions about naming them as well. Remember, this one will be cyclo. This one here is tricky because we haven't done it yet. So maybe ignore D. Oh no, because you are naming it. Okay. Don't worry too much about that one. Okay, because we haven't done that one. This is my year 13 PowerPoint, and obviously at this point they've normally done benzene rings, but you haven't yet. So don't stress about 3D. Do all the other ones for me, okay? Answers are on the next slide, so I'm going to quickly go through. Whoops, there we go. And then you can check your own answers. Okay, so right, reactions, onto reactions. 3 reactions, okay? Oxidation, but remember that only happens with aldehydes because ketones can't oxidize. Reduction, remember reduction's the opposite of oxidation. So if oxidation is removing hydrogens in order to make that carbon double bond oxygen, reduction will go back. So when I reduce an aldehyde, I get back a primary alcohol. When I reduce a ketone, I get back a secondary alcohol. So reduction is kind of like the opposite reaction to what we had before. And then nucleophilic addition. Now, reduction and nucleophilic addition are very similar, okay? Because nucleophilic addition, you break the double bond and add things in. Okay, so in reduction, you break the double bonds and add in hydrogen. With nucleophilic addition, you break the double bond and add in something else other than hydrogen. So these two are very related. The one that you particularly need to know for year 13 is hydrogen cyanide. So I'll come on to that one in a moment. Right, number 1, very straightforward because we've done it before. So aldehydes can be oxidized to form carboxylic acid. So this is the only oxidation reaction that we need to know. If we work it out, so Cr2O7, so if we just work out quick revision of oxidation numbers, okay. So in Cr2O7 2 minus, let me just get this up here, we are to Cr2O7 2 minus. Right, oxygen's 2. Oh, can you see me? Scoot this way a little bit, you'll be able to see it. Can you see it now? Yeah, you can see it now. Okay, here we are. So oxygen's 2 minus, and I've got 7 of them, so that's minus 14, yeah? Overall, I want it to be minus 2, so that's what I want it to be, minus 2 in total. So therefore, if I want it to be minus 2, I need plus 12, yeah? Plus 12 over here, does everybody see that? I've got that's for 2 chromiums, so this one must be 6, plus 6, yeah? So therefore, my chromium 6 plus are reduced to form green chromium 3 plus ions, the orange chromium 6 plus. It says there, why is this reduction? Right, that's the third definition. So remember, oxygen is addition of oxygen, reduction is the removal of oxygen. Oxidation is the addition of hydrogen. No, which way around? The removal of hydrogen, get them the right way around. Reduction is the addition of hydrogen. And then the third one, remember oil rig, oxidation is loss of electrons, reduction is gain of electrons. What's happened here? It's gone from plus 6 to plus 3. It's become more negative. How does it become more negative? The only way is if it's gained electrons. So therefore this must be gain of electrons. Oil rig, a reduction is gain of electrons. Okay. Ketones don't oxidize. Okay, so that's the only one you need to know for oxidation, and that's one we've already done in year 12. So we don't need to stress about that because that's familiar to. Right, on to something new, reduction. So if oxidizing an alcohol gives an aldehyde or a ketone, what do you think reducing an aldehyde or a ketone produces? Absolutely, okay. Remember, oxidation is loss of hydrogen and reduction is gain of hydrogen. So we're basically going back to what we had at the beginning before we oxidized it. So we get back your alcohol, your primary alcohol if it was an aldehyde, and a secondary alcohol if it was a ketone, okay? But in order for this to happen, I need a reducing agent. Now, just remember, we said oxidation is the loss of hydrogen, reduction is the gain of hydrogen. So I need something with lots of hydrogen in there, okay? So this is the reducing agent we use, NaBH4. We also use Li, so lithium tetrahydroborate 3 as well, okay? So this one is the sodium one, but there is also a lithium version of it. So just be aware, you may see both reducing agents being used. Okay, so this is the one I'd like you to remember. Sodium tetra 4 hydrido, there's the hydrogens, borate. This is boron here, 3. Okay, remember that indicates the oxidation number of the boron. Okay. So we've got sodium tetrahydridoborate 3, NaBH4. Now, just the same way that my potassium dichromate is chosen because there's loads and loads of oxygens in there, this is chosen because there's loads and loads of hydrogens in there that we can get rid of. Okay, so it's a mild reducing agent. So it reduces carbonyl groups in aldehydes and ketones, but it doesn't work as a reducing agent for carboxylic acids. Okay. Right, so let's just talk a little bit about how we do this. So remember, it's reduction. We are adding hydrogen to. So it's an addition reaction. Do you remember addition reactions from alkenes? What happens with an addition reaction? The double bond breaks. So what's happening here is this double bond breaks. One hydrogen adds in here to make my OH group, and one hydrogen adds in here to complete my alkane chain, okay? So if I start off with an aldehyde, I'll get a primary alcohol. If I start off with a ketone, double bond breaks, one hydrogen adds in here to the oxygen, making my secondary alcohol. The other hydrogen adds in here to my carbon, completing the alkane chain, okay? So this is what happens, okay? Now, you do need to be aware of the conditions. We use water as a solvent. We'll talk about that in a minute because it's actually part of the mechanism we need to do. We warm it with the sodium tetrahydridoborate. We're going to talk about a mechanism in a minute. You need to include the solvent in the mechanism, and I put there in really big red letters. Remember when we did oxidation? We didn't put the whole potassium dichromate thing in the reaction. We only included the oxygen in square brackets because that's the only bit that's involved in the reaction. In a similar way, something's beeping at the back, ignore it. In a similar way, in reduction, we're only interested in the hydrogen, not the whole sodium tetrahydroborate. Okay, so therefore, we put the hydrogen in square brackets because that's the only bit that's involved in the reaction. Okay, let me talk about the mechanism. I'm sure that we can actually work this one out by ourselves. Okay. I might choose a slightly simpler one than I've got up there, just for sake of you being able to see it. Okay, so here we go. So I'm just going to choose a very simple one here. This is methanol that I've got up here. All right. Now, remember, we said that this is an electronegative. The oxygen is more electronegative than the carbon. So that makes this end delta negative, and it makes my carbon delta positive like this. Okay. Now, this is a reduction reaction, but the mechanism is a nucleophilic addition mechanism. The double bond is going to break, and I'm going to add in my hydrogen. Now, remember, we said my sodium tetrahydroborate 3 is basically a source of hydride ions. Now, okay, let's quick refresher memory. A hydrogen atom has a proton in the middle, like that. Yeah, and then it has round the outside an electron. That's a hydrogen atom. If I make a hydrogen ion, I remove the outer electron, and it becomes positively charged hydrogen ion, just containing a proton and nothing else. That is not what is happening here. Here's my positive ion. Sorry, here's my positive proton. Here's my electron. When I make a hydride ion, so remember anything with IDE on the end, chloride, fluoride, bromide, oxide, etc., is a negative ion. This means it's gained an extra electron. It now has 2 electrons, but only 1 positive ion. Sorry, 1 positive proton. So therefore, this now makes not a 2 minus, 2 negatives, 1 positive, so overall 1 minus. So it's a hydride ion with a lone pair on it. Okay, so this is a hydride ion, and we draw it as a hydrogen with a lone pair on it and a negative charge. Okay, now, quick mention about vocabulary. You know how much I love vocabulary. So this is a nucleophilic addition, okay? Remember nucleophiles? Philios, Greek word for love, attraction, liking. What does it like? It likes nucleuses, positive, areas of positive. What likes things that are positive? Things that are negative. So this is why my hydride ion is a nucleophile. What's a nucleophile? Something that donates electrons to the area of positive charge. Okay, now I've got my pen stuck. Right, okay, now member mechanisms. In a mechanism, where do your curly arrows start? We're using double-headed curly arrows, movement of 2 electrons, okay? 2 places curly arrows can start. Everybody shout at the screen. Okay, good, fantastic. It can either start on a negative charge, or it can start you can start it on a negative charge, but I haven't taught you that one yet. You can start it in between a lone pair or on a bond. Well, I don't have a bond here, I only have a lone pair. So it's going to start in between, so my arrow is going to start in between my lone pairs. It's going to start just there. Where's it going to go to? It's going to go to my positive charge. What's my positive charge? The carbon, okay? So that is going to go up to there, and it's going to make a new bond between this carbon and this hydrogen. Now, that creates a bit of a problem, because if I've got this one making a new bond between this hydrogen and this carbon, I'm now going to have 1, 2, 3, 4, 5 bonds there around the carbon. Carbon can't have 5 bonds around it. So I'm going to need to break one of the bonds. Which bond am I going to break? I'm going to break this bond here. I don't need any extra electrons around the carbon because these two are being donated from the hydride ion. So the electrons are going to go onto the oxygen. Okay, so it's going to go from the bond, curly arrow from the bond, onto the oxygen like that. Everybody see how we got that? Yeah? All right, fantastic. So we've now made a new bond. Let's draw out the intermediate. So I've now made, this is where I need my packs of coloured marker pens. So that's my new bond there. If I had colours, that would be in a different colour, but I don't have colour. Right, that one's going to shift around a little bit to there like that. And that one's going to go up there like that. Now, this one has now gained an electron that it used to share with there. It's now become this one's electron totally. So this one is now negatively charged. Can everybody see that? Yeah? It's gained an extra electron in order for it to be happy. Yeah? Because otherwise it would have missing an electron there and it would want to try and make a double bond again. Well, it doesn't want to do that any longer. It's now got this lone pair, but this lone pair is going to eventually snap or something else. Okay, right, okay, perfect so far. So that's what we've got there, like that. Now then, obviously this is not particularly happy. Can you see that? There we are. This is not particularly happy. So this now needs to bond with something. This is where the water comes in. Remember, it's got water as its solvent. You have to have water in there as well. So I'm going to do it really small in the corner here. You can obviously do yours a bit bigger when you're drawing this out. So there's my water molecule like that. Remember, my oxygen end is delta negative. My hydrogen end is delta positive like that. Delta positive like that. Okay, can you see from my much better diagram on the PowerPoint rather than the one on here? So again, where does my, so it's my negative charge there. Where does my curly arrow go? From my lone pair up to my positive hydrogen. Right, now my hydrogen is now in trouble because it would have a new bond between the oxygen and the hydrogen and the original bond between the hydrogen and the oxygen. So this original bond needs to break. So remember, curly arrow goes from the bond onto the oxygen. And then I just move this one over here like this for the last little bit. Just make that my hydrogen. Hydride rather, not hydrogen. Like that, okay. Right, last step. Okay, so let's just quickly draw out what we've got now. So we've now got my hydrogen there, my carbon there, my O, which has now been bonded onto an H there. Oh, look, what have I made? I've made an alcohol. There's my alcohol. What am I left with? I'm left with an OH minus ion. Okay, there we go. Oops, I'm in the wrong place. You can't see it. There we go. So my products are always the alcohol and a hydroxide ion. Okay, so everybody happy about that? Perfect. Right, let's just click onto that. Now I've messed it up again. So here we go. So that for aldehydes, so what happens? My hydride ion, forgive the curly arrows. If it was up to me, that curly arrow would end there, not there. Okay, curly arrow from the lone pair up to the carbon. That then makes an extra bond between here and here. So then this bond needs to break up onto the oxygen. That now makes this intermediate where the oxygen has a lone pair and a negative charge. That then, this isn't perfect. This would need to have some delta negatives and delta positives on. It goes a curly arrow from in between the lone pair onto the hydrogen. That then makes an extra bond between the oxygen and hydrogen here. So this bond has to break. So curly arrow from the bond onto the oxygen. Here is that. And there's my OH that I've got left. Works exactly the same way for ketones. Okay. Hydride ion, curly arrow up to the delta positive carbon. Double bond breaks. Curly arrow onto the oxygen. Makes this one here with the oxygen negative charge lone pair. And that joins on with a hydrogen from a water to make my now my secondary alcohol, and there's my other product, my hydroxide ion. Okay, is that all right? And I've messed up my PowerPoint. Okay, right. The last reaction you need to know is an addition reaction as well. It works exactly the same way as what we've just done with hydrogen, except for this time it's something that isn't hydrogen, it's another nucleophile. Remember, nucleophiles are anything that are negatively charged. You have a lone pair of electrons that it can donate to the positive charge. Now, the one that you need to be aware of is this one. This is the cyanide ion, okay? Now, we're going to come back to this quite a lot. It's an incredibly useful product. The reason it's useful is it's got a carbon in there. So whenever we add in this, we're actually making our carbon chain one carbon longer, which is really useful when you want to try and make a slightly longer chain than you've got. So what it is it's a carbon, and it's attached to a nitrogen. Now, nitrogen has 5 electrons, yeah, and it wants 8. So when we think about it, that means it needs to have a triple bond between the carbon and the nitrogen. So it's a triple bond between the carbon and the nitrogen, okay? Now, that would mean that the carbon has 3 of its electrons sharing with these ones here, and then it would have an additional electron there, and then it would have 1 electron that it wants. So what happens to it? It gains the extra electron and becomes a negative ion. So this is the cyanide ion. We often, as you can see in my PowerPoint here, this is often bonded to hydrogen. So this is hydrogen cyanide, or it can be sodium cyanide, or potassium cyanide, or something like that. So it will have got the positive, it would have got the extra electron from a hydrogen or a lithium or a potassium or something like the sodium, like that. The sodium will become positively charged, or the hydrogen will become positively charged, and the cyanide will become negatively charged. Right, it's got a lone pair and it's got negative charge. This means that it is a nucleophile, and it can add into my ketone or to my aldehyde. Double bond breaks, mechanism is identical to the mechanism that we just did. But the thing is, you get a different product, because this time, instead of adding a hydrogen, you're adding a CN. So that's quite interesting. So where you used to, so I can see here, where previously that would have been a hydrogen, now you've got this CN. And this whole funny thing here is called a hydroxynitrile. This bit's the nitrile bit, and there's the hydroxy bit. So it's like an alcohol attached to a carbon that's attached to this nitrile group here, okay? So let's quickly look at the mechanism. I'm not going to do it on my mini whiteboard, I think, because it's exactly the same as before. If you're having any difficulties with it, I can go over it in one of our sessions this week. So here's my nucleophile. Curly arrow starts on the lone pair, goes up to the delta positive carbon. The double bond breaks. We form exactly the same as we had before, except for before this was just the hydrogen. Now it's that nitrile group, that C triple bond N that you've got there. Then exactly the same as before. This now then gets attracted onto the delta positive, or the positively charged hydrogen ion in the hydroxynitrile that we've got, hydrogen cyanide that we've got here. So that goes on to there. That bond breaks, makes back a cyanide ion, which can then go and attack another molecule, and so on. Okay, and this is the hydroxynitrile that we make. I'm not going to talk about naming them yet. I'll come back to that at some future point. Okay, in year 30, not now. Okay, exactly the same for ketones, works exactly the same. You can work your way through that. Okay, so great. Quick quiz to check. What is formed when an aldehyde is reduced? Remember, it's the opposite of oxidation. So, remember? Okay, good. You get a primary alcohol. What about when your ketone is reduced? What does it go back to? Fantastic. Secondary alcohol. Define the term nucleophile. Remember, it's something that loves positives. That means it is negative. It has a extra electrons. What's it going to do to those electrons? It's going to donate them. So an electron pair donator. What mechanisms do carbonyls undergo when they are reduced? Nucleophilic addition. What reagents can be used to reduce a carbonyl compound? Do you remember it? Sodium tetrahydroborate 3 plus water. Okay, with an acid catalyst. And a water solvent. What's a nitrile group? That's the carbon triple bond N that you find. Okay, so that makes sense. Hopefully that makes sense. Right, things to try. It's not a lot today. If you have bought your Year 2 chemistry textbook, if you haven't, could you try? I know Miss Malhotra sent you the details of it a while ago and asked you to get it. Really useful, because obviously I'm giving you page numbers there and there's extra things to read up in about it. So have a look at the relevant bits in your textbook. There's some questions to answer in your textbook on page 181, and anything else? Reactions with carbonyl. We're not doing the testing, so I'm not on that bit yet. So only as far as page 182, and then it says sheets, but actually there's only one sheet. Oh, gosh, can I let me see if I can go back to my Teams. Go back. Here's the worksheet for this week. Let me just pop that up on the screen. There we go. Just put that one over there. Okay. So when you have a go at the worksheet today, it's not very long at all. It's 7 questions. Okay. Really straightforward. Okay. So all it's giving you is a compound. This one's an aldehyde. How do I know it's an aldehyde? Because it's the end of the chain. This one's a ketone. How do I know it's a ketone? Because that carbon there is attached to 2 other carbons. Okay. This one's a ketone. That one's an aldehyde. This one's a ketone. Oh, and this one's slightly trickier. Okay. On this one, I've got an aldehyde on that, and then I've got carboxylic acid, which doesn't reduce, remember, on that end. Okay, so what is it asking you? Okay, look at what you've got. You've got a reducing agent here. So we're going to do reduction. What happens with an aldehyde when it reduces? Primary alcohol. What have we got here? Reducing agent. What happens to a ketone when it's reduced? Secondary alcohol. Okay, what's this one? Now this one you're going to get a hydroxynitrile. Double bond breaks, the CN is going to go in there and the H is going to go in here. Okay, similarly with this one, ooh, I'm just wondering whether that one does it like that. Okay, so actually with this one, I didn't actually mention these ones, but it should be fairly obvious. The CN's going to go in there, but then this time I haven't got water, I've got KCN. So actually when the double bond breaks, the oxygen, which is negatively charged, is going to be attracted to the positive K. So you're actually going to have an O with a K next to it there. Yeah? Similarly with this one here, because obviously you've got potassium cyanide rather than hydrogen cyanide, which is the example I gave you in the PowerPoint. Okay, this one again is a reduction. This one here, you're having to put what the reagents. So this one has been oxidized, so think about what your reagents would be. This one has reacted with something that's added the nitrile group in, so think about what that one must be. And that one's an OH over there. And then with this one here, this will be reduction of that one, okay? I have put up the answers as well for you, so do check your own. It should be relatively straightforward. I will meet with you as usual this week, normal times, and do drop into any of those sessions and have a little chat with me. We're doing them with audio now, so if that makes you feel a little bit happier, then you can come along and do all of your questions that way. And so if you've got any questions or anything on any of the other things that we've been doing, please make sure you get in touch. All right, so I'm going to finish that for today, and hopefully that's been useful, and have fun with starting year 13 work. Okay, speak to you later on this week. Okay, bye.